case, I've started recording. You can.
Okay. Today's topic is Bloch's theorem. I don't know how to spell. So I'll first state the problem we want to solve, and then I'm going to do some linear algebra review, which is going to help a lot when we solve the problem. And in the end, only in the end, I'll state the Bloch's theorem, because I think it's more interesting that way. So imagine we have some sort of crystal. I'll just draw a two-dimensional one. So imagine we have some sort of crystal, and then a crystal is defined by, you have these separations, and then by using these two vectors, let's call it A1 and A2, by using these two vectors and adding them up using some linear combination, you can get every single point in the crystal. And then our goal is we want to solve a quantum system that lives within a crystal. So our Hamiltonian is going to look something like, we have some sums of the kinetic energy and some sums of potential energy. And this potential energy is going to be periodic in the sense that this is going to be the same potential, because what we're doing is only translating this to the next cell. These are called cells, by the way. This is called a cell. So what we're doing is we're translating from one cell to another, and since it's a crystal, it's periodic, so we should have the same potential energy. So what we want to solve is solve this Hamiltonian, and mathematically speaking, we want to find the eigenvectors and eigenvalues. Yeah, so let's get started.
Let's stop for one moment.
Sure.
There's like a small assumption here. So.
Not interacting or whatever.
Yeah. So
okay.
First of all,
so
I'm sorry. Let me just say. So first of all, right. So we have some lattice, and any point on the lattice can be written as NA1 plus MA2, where N and M are integers, right? So that's good. Then then this kind of assuming that the potential is periodic, right? What is that really equivalent to? Because at the end of the day, my crystal will have some finite size, right? It will have some boundary. I can, like, if I do some shift of my crystal, eventually I'll go off the crystal, right? If I keep going into enough. So this kind of idea that my potential should be invariant under any shift, I think that somehow implicitly involves me assuming that I assume periodic boundary conditions. So that I'm looking for solutions to the Schrodinger equation that are somehow periodic once I reach the boundary of my crystal. So, yeah. Maybe in other words, it's like you assume that you have an infinitely large crystal so that whatever happens on the boundary doesn't affect what happens in the bulk of the crystal. And so for this reason, you can assume that there's always this translation that you can do. But I think that's also equivalent to just assuming that I'm looking for solutions which are periodic with respect to my...
Yes.
But okay, sure, go ahead.
Okay, so now, well, in solving these kind of questions, it's useful often to think about symmetries. And one symmetry that's given in our thing would be the translation symmetry, translating our entire wave function by these crystal primitive vectors. Is that what it's called? But anyways,
Yes.
yeah, something like that. So we want to find like some sort of operator that's easier to work with than this big thing. So let's start with some linear algebra with commuting operators.
Oh, sorry, let me just make one
Yes.
other comment. Is that so here he's drawing this for a two-dimensional thing because you can draw a two-dimensional thing. But all of the discussion that is going to be done here right now is in a trivial way generalized to n-dimensional lattices.
Yes. If I write on the other board, should I turn?
Yes, you should move the thing and maybe move the cup as well. So that
no, the cup is not blocking.
I would even suggest that you might want to move the table like this once, so that Ife can't see, but then the angle is less. So when Ife watches the recording, she can see better.
Okay, perfect.
Which Ife definitely does. She watches every recording.
Yes, it's all right.
Especially when she doesn't know.
Exactly. Okay, so let's start with some definitions, mostly just notation. So we define this thing to be the eigenspace of the operator T with eigenvalue lambda. And then we define an inner product that's defined on this space V as we denote it by like some sharp brackets. And then an operator is called self-adjoint if the following holds true. Okay, so let's start with the first theorem. If V has countable dimensions, V, how do I write this? Dim V countable. And that T is self-adjoint. Oh wait, yeah, maybe I should say like T is self-adjoint is refers to T star equals T, denoting star as self-adjoint. And that T star equals T, then we have a orthonormal basis of eigenvectors. Does anyone remember how to prove this? Anyone?
Do you roughly remember? I mean, what is this theorem? This has a name.
Well, at least like what's the name?
It is the spectral theorem, and we proved it. Well, I guess in winter we proved it, but
You could do it like just like one by one, grading the space.
say that again.
Once you just like do it like one by one, let's say like starting with the first vector and then like see the space.
That's a rigorous way, but
that is one way to do it.
That is rigorous, but we're in physics, so we don't do things rigorously. So for any operator, we can represent it in some matrix, right? And then any matrix, we can change the basis so that it's some upper triangular. So step one, some matrix of T in some basis equals.
I mean, this is also very rigorous.
Yes, whatever. So this is some upper triangular matrix. And then since T is self-adjoint, and self-adjoint would be, wait, if I use star, then what do I use for complex conjugate?
For self-adjoint, maybe use dagger. For self-adjoint operators, you want to use dagger, and then for T for transpose and star for complex conjugate.
Sure.
It kind of sounds dagger.
Yeah. So adjoint is actually a complex conjugate, and then we transpose it. Doesn't really matter what order we do it in. So this
in an orthonormal basis.
Yes, in an orthonormal basis.
Yes. So
yes.
the adjoint of an operator is equal to the star and transpose if and only if the matrix is written in an orthonormal basis, not otherwise. This you have a lemma that says you can always write any matrix on over complex in general. I forget.
Okay.
What is it? Over complex vector spaces in upper triangular, but then you can always you can use Gram-Schmidt to turn any basis into an orthonormal one, and that will preserve this upper triangularity condition. So in fact, you know that this will always be. You can always write down T in an upper triangular way in an orthonormal basis.
Right.
But then, if T is self-adjoint, you have that statement.
Hopefully everyone understands this. Okay, so this implies that T must equal to both an upper triangular and a lower triangular matrix, which means that everything up here must be 0 and everything down here must be 0, and only that the diagonal is non-zero. And plus, the diagonal is real. So actually, this is just all 3 steps. So only diagonal is non-zero and real and real.
Okay, what's the question?
When you say basis, do you mean like finite linear combination? Because you said the dimension is countable. Are we taking?
Yeah, well,
yes.
Countably infinite is basically finite because you can kind of do it like whatever.
Yes.
You can still write it in some matrix as long as it's countable, right?
You can think of like an infinitely large matrix.
Yeah.
Right? Goes like this, and then remember Gram-Schmidt works for countable
yeah.
things.
We proved it using induction, which means it
yeah, induction means it works on the entire natural numbers.
Gram-Schmidt, Gram-Schmidt works, in general. Because how do you do it? You say let my first vector be take my first vector and normalize it. Then take the second vector, remove the parts parallel to the first vector, and so the second vector becomes orthonormal to the first one. Then you take the third vector, remove parts that are parallel to the first and the second vector. So the third vector becomes orthonormal to the first two. And you keep doing this, and you can keep doing this as much as you like, and you'll end up with an orthonormal set. As long as it's countable, as long as you can index it.
Yes.
Because what you do to this vector only depends on what you did to the previous vector.
Yeah.
And doesn't depend on what you did.
That proves for a finite.
Yeah, but that works for a countable number of vectors too, right?
Yeah, because you're doing induction.
Well,
so
in general, yes, but particularly the way we proved Gram-Schmidt lets it work for countable. And I think for the way you prove, actually, I don't remember how you proved the upper triangular, the theorem about upper triangular. It's like what Scherzbaum or something. What was it?
It's like I remember it like as part of the Jordan decomposition stuff.
No, that's for.
But
yeah.
Yes, but okay. Worst thing we can always I don't know if things are nice enough. Only consider kind of finite linear combinations proof for them, and then kind of expand further something. But okay.
As long as you can write it into a matrix, then you should be fine. Trust.
Yes.
Okay, so this is called the spectral theorem, which is nice. Then I will erase this.
The important result is that if T is self-adjoint, then it has a orthonormal basis of eigenvectors.
Exactly. Yes.
And its eigenvalues are real. Why do eigenvalues need to be real again for self-adjoint operators physically? Do people remember?
When you take the conjugate transpose, like
No, yeah. But I'm asking about
Like physically.
Physically, where did we see self-adjoint operators? What did they mean? And why should their eigenvalues be real in that sense? Yes. If I measure something, it better be a real number. And we said in our partial quantum mechanics that observables are self-adjoint operators.
Where am
And
I
their
shot?
eigenvalues are things we can measure. And we just realized that, okay, self-adjoint operators always have real eigenvalues. And so that's very good, because this means that I can, when I measure something, I'll get a real number. That's very good.
Okay, I lost my chalk. Anyways.
Okay, you have more.
No, I don't like the other few. Anyways. Suppose that S and T are operators on V and that they commute. This is going to be an assumption for the rest of our discussion. First, let lambda be eigenvalue of T. We want to prove that S does not remove any eigenvectors from this eigenspace, which means if we operate S on the eigenspace, it stays inside the eigenspace. Yeah. So how do we prove this?
Okay, you should stop and you should make sure that people understand what the statement is. Maybe you should even draw a picture.
Okay. So let's suppose we have some vector space, and then this is some eigenspace with eigenvalue lambda.
For which operator?
For T. Okay. And then what we want to do is, well, S would be mapping vectors to vectors. So maybe it maps from this point, this vector to that vector. Now what we want is that S only maps vectors from inside the circle back to inside the circle. It doesn't go outside of the circle, which means that, formally speaking, it restricts to this subspace.
Well, that you can infer. Yes.
Yeah, sure.
So the statement is, suppose I have two operators, suppose they commute, then S maps eigenvectors of the other operator back to eigenvectors of that same operator. Okay. And we, once again, we discussed this last year.
Yes.
Maybe not. Okay,
yeah.
Good.
So the proof is quite simple. You just assume there's a vector V inside the eigenspace. And then you look at SV and check if it's still inside the eigenspace. So we act T on it. Since T and S commute, we can write it as STV. So it's S lambda V. And then we can bring the lambda out since S is linear. So again, we have SV is also an eigenvector of eigenvalue lambda. So this concludes the proof. Agree? Maybe? I'll move on. Okay, so the second step is if T is non-degenerate, which means that no eigenvalues would equal, or in some sense. So if two eigenvectors have the same eigenvalue, they must be like multiples of each other, which means that every eigenspace are of dimension 1.
Yes, that's what it is.
So we want to show that there's a basis where both S and T are diagonal. To prove this, we first note that if V is an eigenvector, then S of V is SV is also an eigenvector. But since it's non-degenerate, which means the dimension is only 1, these must be scalar multiples of each other. So we have SV equals some scalar multiple, let's say mu V. So this looks exactly like some other eigen problem, which means that V is also an eigenvector of S. And then once we try all of the eigenvectors for each lambda, we exhaust all of these lambdas, we get a full set of eigenvectors of T, but it's also an eigenvector of S with eigenvalue lambda.
Yes, but
So
maybe a different. So S and T have the same eigenvectors, but then the eigenvalues for those vectors might be different.
yes. So we have found a basis such that both of them are diagonal. Any questions? Discussion? If not, I will move on to the third part. Now, suppose we don't know that it's non-degenerate, but we do know that both S and T are self-adjoint. And V is countable dimensional. We want to prove that there exists some orthonormal basis where both of S and T are diagonal. Okay, so how do we prove this? Well, when we see self-adjoint, the first thing we think of is spectral theorem, which is erased already. So let's start off with applying spectral theorem to S. Yes. So we get a bunch of eigenspaces. So first we know that there's a full set of eigenvectors. And so we do have a bunch of eigenspaces. And we look at one particular eigenspace. Let's do T. Let's apply it to T. Of some lambda I. We look at this subspace, and then we can consider the restriction of S on this space. So consider this operator is again self-adjoint, right? Because it's just a restriction. And also it's truly a restriction because any vector inside this subspace will get mapped back into the subspace. So this is an operator on the subspace. So this is a self-adjoint operator in the subspace. We can again apply spectral theorem to this restriction and get a set of eigenvectors of S. That's also eigenvectors of T with lambda IS eigenvalue.
You should draw a picture again. And you should in fact draw essentially the same picture that you drew last time.
Sure. So these are some eigenspaces. of T. And then each S inside restricted is an operator that maps back to itself. And then, so for each of these subspace, we can apply spectral theorem to the restriction of S to get eigenvectors of S. But these eigenvectors are also an eigenvector within this eigenspace, which means they're eigenvectors of T. So after applying spectral theorem for so many times, we can get a full set of orthonormal bases that's both eigenvectors of T and S.
Yeah. So let me, I want to draw a picture just for fun.
Sure.
With two colors. So the idea is green can be T, right? So I can split up my vector space using T into eigensubspaces. Okay? But then internally, I know that S restricts to each of these subspaces. Okay? So I know S maps from this to itself. So I can restrict S to say this thing, right? And then S is then a some operator that can be that is diagonalizable over here. So then in here I can do a kind of further decomposition according to the eigenvalues of S. Then in here I can do a further decomposition along the eigenvalues of S, and so on and so forth. And so I get a basis of eigenvectors, which are both eigenvectors of S and T. So how is this actually? You've all seen this in quantum mechanics before. This is the idea of quantum blank word that people always talk about. Quantum, and then another word.
What?
So what is this idea? What often comes after the word quantum sometimes? Like in the hydrogen atom, you have two quantum things that you use to label something. Well, what can you use to label things? Just guess a word. Yes, quantum numbers, correct. This is precisely the idea behind quantum numbers. What is the idea? The idea is I have some basis, and the point is I can label this basis using eigenvalues. So that's it. Label basis using eigenvalues. And how would I do this? Well, okay, suppose I have a basis vector for, this thing, right? It's in this green one. It's in the big green blob. And because it's in the big green blob, that means it has to have some eigenvalue, I don't know, lambda I for the T operator. But then it's in like this yellow blob. That means it has to have an eigenvalue of, I don't know, some uj for the operator S. Okay? And so assuming that, okay, maybe S is non-degenerate within this green blob, then I can label everything using these eigenvalues. I can label my entire basis in terms of eigenvalues. And this is called, these eigenvalues are then called quantum numbers because they completely identify which are bases this way. And this is what you do in the, this is what you do with the hydrogen atom, right? You have some Hamiltonian, and so the Hamiltonian has energy eigenstate. But you find out that there's something else that commutes with the Hamiltonian, namely the angular momentum operator. So it's some other operator which commutes with it. And you find, and what you do is you kind of restrict yourself onto a energy eigenstate. And then if you look at a particular energy eigenstate, you see that space is maybe degenerate. And then you find the eigenvectors of this angular momentum operator, which are like what? They're like 0, 1/2, -1/2, whatever. All of these things for the hydrogen atom. And then you find the eigenvectors of that. And essentially, for every energy, you find the eigenvectors of the angular momentum operator. And so you build up a basis of your state space this way by considering things that are both an energy of momentum and this angular momentum of energy and this angular momentum operator. And so, sorry, this is maybe not so clear, but this is what you often do in physics, if you find another operator that commutes with something that's useful, then you can kind of it helps you figure out what the eigenvectors look like.
Yeah.
The eigenvector decomposition.
And also, there's something about if two operators commute, then one of the eigenvalues would be like somehow conserved after like some evolution.
So that is correct.
Yeah.
If something commutes with a Hamiltonian, then it has to be conserved.
If it commutes with the momentum operator, then it's like derivative of x is 0, which is like something like that. Anyways,
but
this is
that
not
is something
important.
You can check from the Schrodinger equation, and maybe
Yeah.
I'll put it as an
like
exercise.
Direct computation. Okay, so the main takeaway of this is that if we have commuting operators, we can find a very, very nice basis that diagonalizes both the operators. So if we have a very annoying operator, let's say t, that we don't know how to solve, we can try and find a commuting operator s and solve for the eigen problem of s instead, which is exactly what we are going to do for this Hamiltonian. Yes. So does anyone want to guess what the commuting operator would be? While I'm erasing.
So maybe let's first recall the state space is the space of L2 functions, right? Or nice enough wave functions
sure.
on our thing.
On each cell, kind of.
No, this can be on the entirety of space.
Sure.
But we assume this periodic boundary condition, or we assume that the crystal is arbitrarily large, whichever one you like.
Yeah.
So maybe write down that the Hilbert space is the space of L2 functions. So just write H equals to curly H equals to L2. L2, and okay.
Yes.
So what should the operator that we have a symmetry with? How should it act on my functions? So we have this crystal that gives us this potential. This potential is periodic. So what operator would commute with H?
Would be a single cell.
As in like what? What's its action on a state?
Not quite, because I don't know what that means. Well,
you have to define what's its action on a state.
Yes. Yeah, you have to tell me if I give you, it's an operator. I have to give you a function, and then you have to give me a function back.
Yes.
Also, if you look that way, it's very pretty.
Yes, I've noticed that. Okay. So a natural one would be some sort of translation operator, because we're naturally given these.
You didn't have them answer. You should have waited for them to answer.
Oh, crap.
It should be a translation operator.
I was distracted.
Okay.
Anyways.
How should the translation operator act on my wave function?
Precisely. So I'm going to use a notation that's different from Wikipedia because that one just sucks. So I have a subscript here.
We should edit the Wikipedia article.
Exactly. So I'll have a subscript here which denotes how much are you translating it. And then internally we will remember that these vectors A should be some sort of linear combination of our crystal vectors, crystal primitive vectors, basis vectors. Okay, so this will be our translation operator. And then let's first check that it's, let's check that it commutes with the Hamiltonian. Okay, so the first term, this is some derivative, which obviously commutes. Like when you translate, you're just translating some sort of translating it into another operator that looks like this, but it just basically is the same as the same operator. Agree? So the first term would commute with the translation operator. The second term, even better, the operator has no effect on this. So it's equivalent to an identity operator on this. Yeah, the action of this operator is basically identity. So sure, that operator would commute with both these terms. So it would commute with the Hamiltonian as well. Okay, so now we want to solve the eigenvalue or like eigenvector.
Wait, do people realize why the translation operator commutes with the derivative?
You add differentiate by something x plus.
Yes.
Yeah.
So because if you do a chain rule, right? X plus a, the derivative of that is still just 1. Okay.
Yeah. So just keep
So
it here.
Yeah, the derivative is just at a shifted point.
Yeah, you can do chain rule and.
Yes.
Okay, so this operator is a nice operator. It's easier to solve than that thing because we don't even know what the potential should be. So let's write down the eigenvalue problem. So we have this thing should equal to, let's label it as this again. Okay, so now we have to think about some conditions for this eigenvalue. Yes. So there are two conditions. So given an operator like this, what can we do with it? We can act it on a function, or we can do something between these operators. We can have a composition of operators. So suppose I have two translations, and this would equal to just the sum of the translations, right? Because they're just vectors. We're just translating by vectors. Acting as a state and writing the eigenvalues, we get some sort of condition that looks like agree? If you want to start guessing what the lambda could be, you can guess like any time. Okay. So this should look a little bit familiar. If we think of lambda as some sort of function that takes in a vector, and then there's this condition. Yeah. And then the second condition is that our states are normalized, right? So we have some normalization condition. Let's just set it as normalized to 1 inside one cell. So inside one cell, we're setting it as, we're normalizing it as 1. But it's also true for the cell next to it, because each cell will have the same volume and have the same, well, the wave function should be physically equivalent. So it should also be normalized, the cell next to it. So we have cell In fact, it would be the same for any sort of crystal translation. Agree?
So there's one comment that you forgot to mention, is that this operator TA, why we're at all doing anything with it, is that this operator is indeed a self-adjoint operator, right? So
yes.
this is an important note. You can probably say it just as well as I can, but I stood up because I wanted to stand up.
That's fine.
So TA is self-adjoint. And how do we check this? So once again, we're working on the Hilbert space, L2. And so what is the inner product on L2? So I'm going to write the inner product for one dimensions, but it's the same for all. Do people remember what the inner product on L2 was? So F inner product G is, yes, so integral from wherever to wherever of F conjugate times G, or the other way around, depending on where you take the linear, which entry you want to be linear. Okay, but now let's check that we can check that T is self-adjoint, and we can also check that T is unitary. So in what sense? So we'll check. I will check that T is unitary, and then you can check that T is self-adjoint on the suggested exercise. But the idea is exactly the same. So how do we do this? Okay, so the norm of a vector, right? That's just this wave function. It's absolute value squared integrated. Okay. But now you can believe me, because we're integrating from minus infinity to infinity. If I was to integrate f of x plus some fixed constant squared, I would get the same integral. Why? Because I'm computing the area under the curve of a function, right? If I shift the whole function to the left or right by a, and then compute the area under the curve, the area didn't change just because I did some shift. Do you agree with this? Yes, essentially, I do a u substitution where I set x to x plus a, and then the Jacobian of that is 1. Okay. But this is exactly me computing TA of f with TA of f. Maybe this should be squared. Okay. Do you agree? You look confused? Do you agree? Or do you disagree? Well, I mean, if something is not clear and you just don't understand what is being said, that is fair.
What is unitary?
Unitary means this, that it preserves the metric. It preserves the norm. So,
or like
unitary means TF is equal to FF.
Yeah.
Well, in this case, we'd actually have TFTG is. So actually, this means so you have this condition.
And then the consequence would be the adjoint would equal to the inverse of the operator.
Yes.
Yeah, so you can think of it as like some sort of rotation in some higher dimensional space, like kind of. So it preserves whatever lengths the vector had.
Actually, in this case, we would have so it's not TA is not self-adjoint. It's skew adjoint or something like this.
Close enough.
Yeah, or it's not. Yeah, it's not quite self-adjoint, but the spectral theorem for it still works, right?
Because spectral theorem works for like normal operators.
Normal operators,
so
correct.
It would work as well.
So this is a lie. Sorry, I lied. This is not self-adjoint. It's not self-adjoint. It's unitary, but it still has spectral theorem.
Yes. Unitary implies normality. Normal operators is like a much weaker condition.
Normal operator means it commutes with its adjoint.
Yes.
And in this case, we do have that it commutes with its adjoint because its adjoint is going to be shifting by minus a, which you can check by doing the change of variables of the integral. The adjoint is shifting by minus a, and we showed that t of a plus t of a applied to t of a prime should be t of a plus a prime, and so t of a should commute with t of minus a. Well, it should just be the do nothing operation.
Okay. So back to our condition. For this part, we can substitute our eigenvalue problem. So this one would be some lambda a vector and then psi of r. So what do we get from this condition? We get the norm of lambda a vector is always 1. Agree? Yeah. Am I missing it? Yeah, for all sorts of translation, as long as it's within the lattice linear combination. Okay, so from this condition, we can always write this as some sort of complex number that is with magnitude 1. So this one would be some e to the I phi of a vector. And then if we put this back in here, we get e of I phi a prime plus phi a, oh, the prime should be this side, equals e of phi, yeah. Yes.
So essentially, we want to use this we want to use eigenvalues to find eigenvectors of t to then solve h, which
exactly.
Once we run into a problem of like that the eigenvalues here like are not necessarily real.
Yes, because a translation operator is not a measurement. So if you remember, only operators that have a measurement should measure out real values.
And they would be self-adjoint. And
yes.
As with this, as we just pointed out, it's not self-adjoint.
Yes.
Yeah, but like, can we still use it for the purpose of measuring? Like,
no, because it's not self-adjoint.
Yeah.
So we're not measuring h.
Like not measuring, like get the eigen.
It's a
yes, why not?
It's a way of getting eigenvectors out. And
yes.
Since these are eigenvectors of t, which commutes with h, they would also be eigenvectors of h, which means we can represent the entire eigenspace with these eigenvectors. So we're mainly just using the eigenvectors of t, and the eigenvalues are maybe just for labeling the eigenvectors.
H will have eigenvalues which are real. This may have complex eigenvalues, but I can still use complex numbers to label my states. Right? This is a statement I'm saying that I'm labeling something. I can label anything with whatever I want. Now, one thing that we might need to be a little careful here is that so if TA has degeneracy, then an eigenvector of TA is not necessarily immediately an eigenvector of H. We need to then restrict H onto the eigensubspace and then do this. But in nice cases that we will usually consider, you will see that TA, the spectrum of TA is in fact is non-degenerate, and even if it is degenerate, then we will like from the get-go write it in such a way that it's immediately an eigenvector of H, because we will just write it very nicely.
Too much spoiling.
Yes.
Anyways, and also if it's degenerate, we do run into some problems, but you can also prove that you can just switch to another basis and then the problems would disappear. If you're interested, you should read the book that's suggested on the last line of Ivan's suggested reading. Yes, which is a pretty nice book. So from this condition, we can see that phi is some linear function, right? If it's too small, I can write it bigger. so this phi is a linear function, which means that we can just write it as some sort of linear combination of the components of A, which I'll just write it as some real vector dots A for some real vector. Agree? The reason why we call we call it K would be obvious soon. Maybe not today, but yeah. Okay, so now we got the eigenvalues are really just something of this form, which looks quite familiar already. It looks like a plane wave. And so yeah, that's the Bloch theorem. The Bloch theorem states how should I do it? Actually, do I have to state it? I mean, that's pretty much.
You should still state it.
That's the idea. I don't quite know how to state it. Like Wiki has two ways to say.
Let's think of it and state it.
Let's write it up there actually.
So
So the statement, there's two versions. The first one, version 1, is that there exists a basis that satisfies two things. The first one are eigenvectors of H. The second one are Bloch states, where Bloch states mean some e to ik dot r and some u. This is capital U, this is lowercase u. It can be written into this form where U is strictly periodic, which means where, I should erase some stuff. Is everyone fine with erasing these words? Where U is strictly periodic, which means this one equals to whatever crystal translation we have. This is version 1. There is a basis that satisfies two things. The second version is there exists K, a vector, in whatever dimension our crystal is in, such that translating by some crystal vector amount would be multiplying by some phase shift. This is what we've proved just now. And then you can show that this is equivalent to stating this, which I should leave as an exercise because I haven't done that. Yes. Should be pretty obvious. And this is Bloch's theorem. But wait, it's not finished yet. There's a problem. We have a problem, which is
You should give them a moment because they're still writing.
Oh, okay.
And because they're still writing, you should so as a presenter, you look down and you see that they're all still writing. And so then maybe they need more time. So you have a cup of tea placed in front of you for a reason.
Exactly, yes.
So you stop and then you take a sip of tea. And that's like the whole point.
Great.
Of all of it.
I don't want to erase this. This looks too good.
That's crazy.
Should I be drawing those Brillouin zones? Like whatever. That's kind of cute.
We could, but we should first, introduce what it is, and then maybe we can
yes.
And why it makes sense.
Okay.
Sorry. Actually, I'll interrupt you once again. So, what did we achieve, right? So we had these TAs. They commute with the Hamiltonian, so they should have the same basis of eigenvectors for various reasons. And we found out that the eigenvalues of these TKs are these exponentials e to the I k dot a. Okay. That's what we realized. We realized that we proved version 2, but version 2 turns out to be equivalent to version 1.
Yes.
So version 2 we proved, and we got that t of the eigenvalues of applying t of a on my wave functions on this basis of wave function should be a complex exponential, and I can always write it as e to the I k dot a. Okay. Now that's great, but
what have we achieved?
Yeah, so what's the point of writing this? What's the point of writing this as e to the I k dot a and not anything else? Because now I can label my eigenstates with these vectors k. Do you agree?
Well, technically you would label it with the eigenvalue, but since the eigenvalue looks exactly the same for every eigenvector, then you would label it with k, which I've done already.
Yes. So now I can say that okay, I can label my eigenstates by my energies E, and also if there's some degeneracy by K, by momentum K. And this is a very big achievement.
Not really. Well, when I was reading, I didn't see the point of this at all. Like,
that's fine.
Sure, you have some phase shift, but shouldn't that be like physically equivalent? And you really have achieved nothing. Well, the problem comes from this k. You can really pick any k. If you look back at here, back at phi being linear, the choice of k is really arbitrary, which means any k would suit as an eigenvalue, right?
Well, not quite. No. So I have my TA, and I know that let phi k. So let psi be an eigenvector of TA. I know that TA applied to psi will be some e to the I phi multiplied by this, and then if I want to, so that's fixed, and then if I demand phi a to be k dot a, which I can do, then k can't necessarily be anything because I still need it to be an eigen value. I still need to get e to the I phi of a.
Yeah, as long as it's real.
Yes, but so I'm not necessarily guaranteed that k can be any number. So I'm not necessarily guaranteed that for any number I'll have an eigenvalue.
No, like sure you can have a k and then you can dot it and then you raise it to some exponential.
Well, you'd need to actually check what the Hamiltonian is, and that this will indeed be an energy eigenstate.
Okay, yeah.
So
sure.
I can always write something.
Yeah, sure.
I can always write something down which will be an eigenstate of the translation operator, but then it might not be an eigenstate of the Hamiltonian.
Sure.
So if I want it to be both an eigenstate of the Hamiltonian and the translation operator, I can't have exactly any k. However, you can notice that you can, in principle, you know that you will have some k, but the problem is the choice of that k is not neat. I can always
Yes.
add, and this is now where you.
Okay.
So,
So
there's the small caveat.
as we can see, the eigenvalue is this thing, which means that we can have different k's that gives the same eigenvalue, which means, yeah, I'll give you an example. For example, I have.
So sorry, what property of the complex exponential are you using?
I'm using some properties with vectors, which I can have a vector
No,
that's.
that's not.
I know. This is like the basic example.
No. You should first say that e to the I of 2 pi is equal to.
Well, that's the next step.
Okay.
So like the first thing is 0, of course. This is the
Okay.
base case. So I can define some vector that is like orthogonal to A, which means it dots to 0. And k plus capital K would give the exact same eigenvalue. Right?
Yeah.
But we don't have to only have 0 here, because we have we know that e to the 2 pi I, wait, what? 2 pi I is 1. And also we know that if it's multiplied by some integer, it's still 1. So we technically can pick this to equal to some 2 pi, let's call it m, actually. N. Sure. Yeah, and then it would still give the same eigenvalue. So why is this interesting? So let's look at a one-dimensional case. Yeah. So in 1D, we have the eigenvalue is just IKA, and then this is K. And then suppose this is K, this is K plus capital K. Oh wait, no. If it's one-dimensional, we can write that capital K is 2 pi n over a, like any sort of numbers in the form of this, where n is some integer.
So the standard notation is to denote these vectors with G.
G.
Capital G, because they're reciprocal lattice vectors and people use capital G for that.
I've seen somewhere it was K, but anyways.
I mean, this book probably uses K because it's like from 1972.
Okay, sure. Let's use G. Yeah, we'll get to that. But I mean, like small k and large k, that's kind of symmetric. Yeah. That's kind of nice. But yeah, so let's say this is 0. This is k. This is k plus g, and then k plus 2g. Let's just say this is n equals 1, and then we can always like plus 2g, plus 3g, whatever. And then here's minus k, whatever. So what we're saying is these eigenvalues are really the same, not 0. They have the same eigenvalue of this form. So we can always pick k such that it's smaller than, wait, what? Yeah, we can always pick k such that k is in between 0 and capital G by keep on taking away g from this k. Agree? Yeah, we're doing it in 1D. Suppose we're doing it in 1D, yes. So it's the crystal would be just a one-dimensional number line with like 0a, 2a, minus a, minus 2a.
We have a chain of
crystal
atoms which are with spacing a between them.
Yeah. And then what's interesting is that if you look at this number line, it looks like another crystal. what you're saying is that these points are somehow equivalent, as in that they give the same eigenvalues. So what we call this the reciprocal lattice, which is, you can think of it as the real lattice, but in the momentum space.
Well, we define
Kind of.
momentum space this way. So,
well, yeah.
What was the idea? We had an original lattice, right? And so that gave rise to some potential, which we assumed should follow the periodicity of the time. So then we got this Hamiltonian. Then we said that we should have these translation operators, which should commute with the Hamiltonian. And so we can write down a basis in which the Hamiltonian and these translation operators are simultaneously diagonalizable. So it makes sense to look at an eigenstate of the translation operator. And the eigenstate of the translation operator will have some eigenvalue, which we proved has to be a complex exponential e to the I phi. And then we argued that this phi has to be a linear function of the form k dot a, where a is the direction in which I translate. And so we said, okay, instead of labeling the eigenvalues, the eigenvectors of TA using the eigenvalues, let's instead label them using these k dot a, where k corresponds to an eigenvector of t with eigenvalue e to the I k dot a. Okay, so let's label our eigenvectors using k, where the eigenvector labeled by k is the eigenvector of t with the eigenvalue e to the I k dot a, of ta with eigenvalue e to the I k dot a. Do those words make sense? Okay. But then we see that this choice of labeling that we've made for our eigenvectors is not a unique choice. So multiple different k's give me the same eigenvalue and therefore label the same eigenvector. Okay, and that's an interesting idea.
Did I do something wrong here? Because I feel like it should be like, I can make it so that it's in the, yeah. I should like make it like in the neighborhood of 0 instead of like 0 to g.
In the neighborhood of 0, yes.
Yeah, so it should be like g over 2 or something.
So the way that people explain what the first Berlin zone is they usually do this geometrically. You could do g over 2, but you don't do it by norm. It's a little non.
Yeah, I know, but in like one dimensional.
Yeah, in one dimensional you do g over 2 minus g
we
over
can
2
pick this, but we can also subtract one more g, so that it's between g over 2 which is easier to work with if we go back to a real lattice, like in multiple dimensions.
Yes.
Yes,
because
exactly.
Then the edges would be identified.
Yes.
So what you're trying to do with this Berlin zone business is, okay, I am trying to label my eigenvectors using my eigenvalues using k. Okay. However, I find out very quickly that choices of k, which differ by this reciprocal lattice vector, give me the same eigenvalue. So k and k plus g correspond to the same eigenvalue, which is a problem. So I should restrict my attention only to the to a region where no 2 points are equivalent. And so the way that we choose this region by convention, and we call this the first Berlin zone, is something that is so we only look at numbers k, which are from minus g over 2 to g over 2. And that ensures in that region there will be nothing that's equivalent to itself. Why? Because I say things are equivalent if and only if their difference is g, right? And no 2 points have a difference of g or more if they're within that region. And the other thing I realize is that anything outside of this Berlin zone will be equivalent to something inside the Berlin zone.
We still need one non-strict.
Yeah, one should be non-strict. Pick a random one.
This one.
Okay. Sure. No one cares.
Exactly. Okay. So let's go to the three-dimensional case, or like two dimensions or three dimensions.
Let's do 2 dimensions because 3 dimensions is hard.
It's
And
not.
then-
I'll just say it's a given, and then you'll check whatever
Yes.
yourself.
And then maybe you'll do say.
Can I erase this? I mean,
give them a moment. Sure. And then maybe do the square lattice for them, and then
let them draw. Let them draw it. Yes.
Correct. In fact, this will be essentially a problem that I just had on my problem set.
Yes.
That's due tomorrow. Yeah, it's a very easy question. It's a,
but
you
are
have to
you
draw a picture, and so it takes. I've practiced drawing pictures many times.
Are you drawing it on LaTeX or?
No.
by hand?
I mean, I could. I know how to, but why would I?
Exactly. Yes.
Who cares? I'll draw it by hand and submit that.
Okay. Wait, maybe like a side note, like why this would be interesting. Apart from, we have some crystal we can define in the momentum space. Well, why is it called momentum space in the first place? Is because when we act a momentum operator on a state that looks like this, you're gonna get some product rule, and then you're gonna get some k down, which means that k is related to the momentum of whatever wave function that's living in your cell. Which means k represents some sort of momentum, like physically measurable momentum. And here we already said that these k's are equivalent, which means momentum are also equivalent if you just like keep on adding. Which means well, energy is dependent on momentum, and momentum is like kind of periodic, which means energy is also like somehow periodic. It can't go to infinity because usually you just have p. I just realized I missed this square the entire time. Anyways, so usually you have h equals some p squared over 2m, and as momentum grows, energy will grow indefinitely. So technically you can have infinite energy if you have like infinite momentum. But here, in the crystal case, this is different. Because as you increase your momentum, because of this crystal structure, you're getting back energy. You're repeating the energy you've gotten before, which means all the energy can be identified with the first zone. So energy would be, it will have some sort of upper bound and lower bound. This is called the band structure of this crystal. Yes, I do not know what I'm saying, but very much.
The words are kind of right, quite a bit wrong.
Yeah.
Because in one sense, like if I had some infinite dimensional Hilbert space, then in principle my energy need not be bounded, because I could have in my Berlin zone, I can have each band is going to be bounded, but I can have infinitely many bands which go up to higher and higher energies.
Okay.
So that's not true.
Okay.
But
whatever.
Essentially, from everything he said now, you should believe him that k kind of looks like momentum,
Yes.
and so this is maybe saying something about momentum. But more on that will be discussed next time, where we'll actually talk about it properly.
Yes, I do not know what I'm saying.
Yes.
Okay.
Let's. I will. Do you have anything else to say?
Promoting it to 2 dimensions.
Oh, promoting it to 2 dimensions.
Do we have the time?
We have the time, but maybe I don't care. And you'll do this as a suggested exercise. Promoting this, you should really do this suggested exercise for this week, because it will be very helpful for what we're going to discuss over reading. But okay, what Janet is going to discuss over reading. And I just want to make a general remark about something. So okay, I will say the same thing I said like 5 times at this point. So we have the Hamiltonian. We have this TA's degree. We found, we said at the beginning we had some theorem. We showed that we can have some kind of things which will be eigenstates simultaneously of H and this thing. That was the kind of theorem at the beginning. And then we argued that if this is an eigenvector of this, then the eigenvalue can be written like this, necessarily, okay? And then this is some, okay. The eigenvalue necessarily can be written like this. We got this from the normalization condition, right? So the fact that it has to square to 1, we got from the normalization condition. Okay, very good. Now, we said, okay, let's label. So you use this K to label our eigenstates of TA. Okay? And note that this TA, this is not one operator. This is many, many operators for different A's that I can have, right? This A can be any linear combination of A1, A2, A3. Okay? So, in fact, here we simultaneously diagonalize like infinitely many operators. Well, countably many operators, right? Because I can translate like 2 this way, or 3 this way, or by 4 units this way, and so on and so forth. Yeah. And we found something that's an eigenvector of all of these translation operators at once with eigenvalue mu. We said that you can always rewrite mu as e to the I k dot a, where a is, how much I'm translating by. And so it turns out that for all of these translations, I can label this eigenvalue using this k. Okay? So I can label my eigenvectors by my eigenvectors of my Hamiltonian by some number, by some vector k. All right, so this is the point. But the point that we find out is actually that these k have this weird thing that the eigenstate for k will be the same as the eigenstate for some number k plus some vector g. Right? And this is because I'm using k to label the eigenstate associated with this eigenvalue. And if I shift k by just the right vector, I will get a 2 pi I, and that will not change the eigenvalue because that's just going to be 1. Okay? So I have this redundancy in how I choose to do this labeling. Okay? And so because of this redundancy of choice, I get that, when I do this labeling, k is equal to k plus g. So what you in principle could think of, this is where we're going back to this whole idea from the very beginning that I mentioned on day 1. That what you could think of is, okay, these numbers k, they come from some space, which will be some manifold. Okay, which will be some manifold. And you realize that when I write down coordinates for this manifold, in these coordinates, the point at k will be the same as the point at k plus g. Okay? So in fact, this manifold is not just going to be Rn, it's going to be something non-trivial. It's going to be a manifold where some points are somehow equivalent to each other, so this is going to be some quotient space of Rn. Okay? And at every point, I have this eigenvector of k. So in this case, we have one eigenvector, but later we'll see cases where I have multiple eigenvectors that are labeled with the same k, and so then I have to use the energies to differentiate this labeling, and that's where I get the bands. Okay. So at every point, I will have some eigenvector. Do you agree? And so using this approach, I kind of know that my eigenvectors can be labeled by k, but then I realize that some eigenvectors will be the same. So then this space of allowed k's will somehow have to be, something non-trivial topologically. In the one-dimensional case, we got that it has to be a circle, right? Because what did we get? We got that, 1k is equivalent to some k plus 2 pi over a, right? Something like that. Okay. So then I know that this point is equivalent to this point. All these other points in between are inequivalent. But if this point is equivalent to this point, that's just the same topologically as a circle. Do you agree? So my allowed k's live on a circle. So this is S1. And so I get that I can use labels that only come from S1. But then I have this eigenstate at every point. So at every point on my circle, I have some eigenstate. So I attach at every point a vector space. And so I get this vector bundle where I have S1 cross I guess a one-dimensional complex space, cross C, right? And so I can actually, what I just did is I took my total Hilbert space and then kind of split it into these slices according to my momentum K and rewrote it down as a fiber bundle. And this is where all of the interesting topology comes in. Because what I managed to do is I took a vector space and then I foliated it into a vector bundle. So I had a vector space. So if you don't understand what the word foliate means, it doesn't matter. No one cares. What matters is, I'm going to try and draw a picture again, is that I had my vector space. Do you agree? Then I managed to split it off as a direct sum of eigenvectors, and I labeled these eigenvectors by k1, k2, whatever, by some vectors k. Do you agree? And then I said, okay, I can look at just this subspace, and I can rewrite this as kind of, this will be the same. I can turn this and split it up based on these k's into a space where I have a space where k labels live cross some vector space. Right, so I kind of took a vector space and used labels to kind of split it up into these pieces and then glue them back together somehow to get this completely different object where I have some numbers, and at every number I have a vector space attached to it. Okay. And so this procedure is where we're going to get all of this topology from, to be able to talk about topological bands and topological insulators and all of this. We're taking kind of a vector space object and then turning it into a geometric object using this kind of funky construction. But okay, if you don't understand all the words, that's fine. You can either ask a question now, or you can wait for me to stay up all night and type up suggested exercises for you, where you'll have one problem which will hopefully clarify a lot of things. Okay. Or you can ask a question. And this is where I stop and have a sip of tea. And there's nothing in my cup.
That's crazy. Surely there's still in the
There's
pot.
a lot left. Okay. Yes.
Like all this was initially done to solve the Hamiltonian.
Yes.
So
Yes, we still haven't solved
Well,
it.
you know, to solve the Hamiltonian, well, I need to tell you exactly what the Hamiltonian is and then solve it, right?
Yes.
If I was able to give you an explicit solution for an arbitrary Hamiltonian, well, then physics would be a much simpler subject, and we wouldn't need to care about all of this.
I need, but like, does it even bring us closer to like?
Yes, it does.
Yes. I'll give you a quick example. For example, if you have the crystal potential as some delta functions, which just means that the electrons can't be on the lattice points, but it can be anywhere else. Then using version 1, you have small u would be just 1. And so every electron inside each cell would be some plane waves. Yeah.
So,
which is just equivalent to like having a bunch of square waves and you solve it inside.
so I told you, like, we told you that you can find the, that the eigenvectors of this TA thing have to the eigenvectors of H have to, well, can be, you can choose a basis such that the eigenvectors of H and the eigenvectors of these TA operators are the same, but you can show that the eigenvectors of this translation operator can be some complex kind of exponential dot some periodic thing. So in principle, I just told you what the eigenvectors are. It's just that not all of the eigenvectors of TA will necessarily be eigenvectors of H, but then you can figure out which ones are. And what we will see with these tight binding models, what Janet will talk about during reading week, is going to be precisely this example of us taking a particular Hamiltonian, though it will be sufficiently general, and explicitly solving using this method by knowing that, oh, if I go to this basis of plane waves, I'm guaranteed to get eigenvectors of the Hamiltonian. So essentially, now you know that if you were to go into this plane wave basis, your Hamiltonian will look diagonal in this K-space basis. So this theorem tells you in which basis the Hamiltonian will be diagonal. Like it tells you what the eigenvector should be, and then if you know what the basis, then you just have to do a change of basis, and then you'll get the eigenvalues in an easy way. Yes. Okay. There will be a bit more discussion on this. And yeah. Okay. I'm going to stop.